Welcome back to week 3 of our course Boltzmann Law Physics to Computing. This is the third lecture of this week. Now, what we'll be doing, I guess in the very first lecture of this week, we introduced this transition matrix and this way of finding the stationary probability distribution from the eigenvector with the eigenvalue of 1. And what we did in the last lecture is we saw how to write down the W matrix for this sampling procedure that we have been using in general in this course. Now, this lecture is kind of a continuation of the last one, and what we'll try to do is compare what you get when you update neurons sequentially and what happens when you update them simultaneously. And the W matrix gives you a nice analytical way of seeing those results. Now, the toy example that we used in the last lecture, that's again 2 neurons. The energy is given in matrix form like so, and you can go ahead and write down the energies for all 4 configurations: 0, 0, 0, 1, 1, 0, and 1, 1. Now, using this, if you want to calculate the histogram, the probabilities of these different states, you'll get something looking like this. And you could use the Boltzmann method, or you could use the sampling method that we talked about earlier, and they match very well. And here's an example with x, the bias vector being -1 for both neurons, and the weight matrix having 2 on the off diagonal. So that's the interaction term. Now, how do you see this shape? Well, the easiest is in terms of the Boltzmann distribution, because as you know, the Boltzmann is exponential of -e. So what you need to find out is the energies of these different configurations. And if you put in the numbers, you'll see that 1, 1 has the same energy as 0, 0 for this choice of parameters. And so 0, 0 and 1, 1 have exactly the same probability. Whereas 0, 1 and 1, 0 have a lower energy. They are -1 each, and so they have a higher probability. So these ratios would be like, e to the power 0, e to the power -1, e to the power -1, and e to the power 0. And then, of course, you have to normalize them so that all probabilities add up to 1. So that's the straightforward procedure of how to see the answer you are expecting. Now, if you change the bias a little bit, like -0.5, well, then these energies come out a little different. 1, 1 now has a slightly higher energy than 0, 0, and so its probability goes down. And 0, 1 and 1, 0 are also not equal anymore. 0, 1 has a lower energy and hence a higher probability. Okay, so that's the toy example we are using to try out these concepts of the W matrix and the update sequence and simultaneous updating, etc. Okay. Now, if we want to write down the W matrix, then that's what we did in the last lecture. We spent some time writing W1 and W2. W1 is the W matrix for updating neuron 1, keeping neuron 2 fixed. And W2 is the transition matrix for updating neuron 2, keeping neuron 1 fixed. And as you can see, these involve these different Fermi functions, and the Fermi functions are determined by these energy differences. So F1 corresponds to this difference between 1, 0 and 0, 0, whereas F2 is the difference between 0, 1 and 0, 0. Whereas they also have a F1 tilde and an F2 tilde where the interaction terms are involved. It's the difference between 0, 1 and 1, 1, or 1, 0 and 1, 1. Okay? So that's what, so the tildes are like the ones without the tilde, except that the interaction energy is involved. There's W1 too. Okay. Now, how do you apply it to the problem to calculate the stationary distribution? Well, first you have to write the composite W matrix, which you could do either if you assume that you first update 1 and then 2, then you'd put the W1 first meaning to the right, because that's the one that operates on your distribution first, and then W2. Or if you update 2 first, then that's the one on the right, and then W1. And this product then is the new W matrix, and if you then find the eigenvector with eigenvalue equal to 1. And if you do that, you'll get results that will match the Boltzmann result very nicely, Boltzmann result and the sampling result. So I've now added this third method, the W matrix method. You see, the first two methods we had in week 2. This W matrix method is what we are adding now. And once you have set up the matrix, you can just find those eigenvalues, the eigenvectors, and you'll find that they match perfectly. And I'm showing both the examples that I talked about. They have the same weight matrix, but slightly different bias vectors. Now, what I want to talk about is what it would look like if instead of updating them one by one, I were to update them simultaneously. That means, say I've got 1 and 2, and I calculate what is the probability of this neuron being 0 or 1 at the next step, and we calculate the probability of what's the neuron 2, what the probabilities are. But then instead of updating just one of them, let's say I'm a little impatient and I say, no, let's do it quickly, update them both. Why not? Right? So I have an F1, so supposing I'm in 0, 0. So I could go to either 1, 0 or to 0, 1. And for going to 1, 0, you'd have a Fermi function whose this x1 is determined by energy difference between 1, 0 and 0, 0. Now, here the energy difference is determined by between 0, 1 and 0, 0. That's the x2. Right? So now the sequential method, we'd of course have updated only one of them and done nothing with the other one. But now let's say we decide that no, let's do it together. So the probability that I'll put them both in 1 is F1 times F2. Because F1 is the probability that neuron 1 will be 1, F2 is the probability neuron 2 will be 1, and so the chances that both are 1 is F1, F2. Similarly, the probability that it's 1, 0 is F1 times 1 minus F2. 0, 1, well, 1 minus F1 times F2. And 0, 0 is 1 minus F1 times 1 minus F2. So that would be the W matrix for simultaneous updating. Okay, I guess that's the first column. If you want to write the second column, 0, 1, then I guess we'll have to invoke another Fermi function, the one that corresponds to going from 0, 1 to 1, 1. Right? Because from 0, 1, if I change the first neuron, it becomes 1, 1. If I change the second neuron, it becomes 0, 0. So the two Fermi functions involved would be this F2 and the F1 tilde. And so you can see the way these terms are, they look exactly the same, except that now instead of F2 and F1, we have F2 and F1 tilde. That's all. But otherwise much the same structure. And F1 tilde, because you see your initial state already has 1 in the second neuron, and because it is 1, the first one kind of feels this interaction energy. So the x is a little bigger actually. Similarly, if you want to fill up 1, 0, then what you find is again same structure. As far as 1 is concerned, there is no tilde, but the 2 now has a tilde. So the 2 is now corresponds to something that has the interaction energy in it. And finally 1, 1, where they have both have the tilde on it. Okay? So that is the W matrix that would correspond to simultaneously updating the neurons, both of them, right? And you could, of course, do the experiment on the computer by updating them simultaneously, one after the other, over and over, or this W matrix gives you a kind of an analytical way of describing this. Now if you compare, you see, here I'm showing again the three methods, the Boltzmann method, the sampling method, and the W matrix method. And the sampling now is not Gibbs sampling, but it's this simultaneous update method. You'll notice the sampling and the W matrix, they match exactly. So the yellow and the green, they are matched very nicely. So that tells you that this W matrix method actually describes this sampling procedure very well. Okay. But you'll notice they don't match the Boltzmann answer, which is this blue peak. Right? So when you do simultaneous update, whatever stationary distribution you get by sampling will not look like the Boltzmann distribution, which is what you want, of course. And that's why the simultaneous updating is not used at all. But what works very nicely, we have seen, is this sequential updating. You could do W1, W2 or W2, W1, and in either case it matches very nicely. So you might wonder, well, what does this matrix really look like compared to the simultaneous updating? Why is it that one's working beautifully and the other's not working? And you'll notice the differences are pretty subtle. You see, if you actually took our W1 and W2, and it's a bit of algebra, but if you actually multiplied out those two matrices, you'd get something looking like this. And again, if you did W2 times W1, it would look a little different. But again, the basic structure is very similar. But it's just that the tildes are in different places. So for example, here, the first column had no tilde in it. Here, the first column does have a couple of tildes, and so on. Okay? So these are subtle differences, and yet it leads to a major difference here. Now what you might wonder though is that, of course, the difference between the pure F1 and the F1 tilde really comes from the interaction term W12. What would happen if the interaction were 0? And the answer is, if we set the this interaction matrix, the weight matrix, to 0, sure enough, they all match the Boltzmann nicely, because then you see they're all much the same. But this is kind of the trivial situation, that is, where you have a whole bunch of neurons that don't know about each other. And in that case, it really doesn't matter whether you updated them sequentially or all simultaneously. They're all independent anyway, so why shouldn't? Right? Now, but there's one very interesting principle that I want to just talk a little bit about before finishing up. But let me just mention then the facts that we know now. That is, that if you do it sequentially, it doesn't matter what order you do it, they will both match Boltzmann. If you do it simultaneously, it will not match Boltzmann. And of course, this is unfortunate because the simultaneous process is something you could do very fast because they are all in parallel. Sequential means it's slow because you have to do it one by one. Of course, 2 neurons, it doesn't matter, but when you have 1,000,000 neurons, it matters that you have to update them all sequentially. Okay? But the simultaneous one does work if the neurons are unconnected. Now, one can make use of this actually in the world of Boltzmann networks by defining something called a restricted Boltzmann machine. What they do there is all the neurons are put in 2 groups. So here, by the way, previously when I drew pictures like this, the horizontal axis was time. Here it's not time. Here is just a whole bunch of neurons. That's all. And they are divided into 2 groups, the A group and the B group. And there is no connection internally among the A group and no connection internally among the B group, but there's lots of connection between the 2 groups. So when I look at the transition matrix, it will be almost like the A set, and not the transition matrix, I mean the weight matrix. The weight matrix has 0 connections between A and A or B and B, but it has all the connections going B to A and A to B. What's the advantage? Well, what this means is now I can update all neurons in group A simultaneously because they have no connections amongst them. And so whether it's simultaneous or sequential doesn't really matter. And I can update all of group B simultaneously. But then, of course, I cannot update all of them simultaneously. So, but this is a big advantage because if you had 1 million neurons, half in group A, half in group B, it means you could update 500,000 and then go on to the other 500,000 and back and forth like so. Right? And this is something that is often people make use of this idea in many different contexts. This is this checkerboard pattern. That is, it's almost like you have a chessboard with some white squares and black squares, and there is no connection among the white squares or connection among the black squares, right? But only connections are between black and white. And this is something that has great practical utility because it can speed up this process enormously. Okay. So that kind of, I guess, wraps up what I wanted to say in this context, that using this idea of transition matrices, trying to show you why certain update patterns work and some update patterns don't work, and why it is important to update sequentially when neurons are connected. Now, what we'll do next is talk about Bayesian networks. What that means is all our discussion is about Boltzmann networks, where W12 is equal to W21. But there is a whole class of networks where the connection is one way. And there you'll see there are some interesting twists. For example, the update sequence actually matters. Whereas for Boltzmann networks, it doesn't matter whether it is 1 and then 2 or 2 and then 1. But in Bayesian networks, it does matter. And that's what we'll pick up in the next lecture. Thank you.